Jnanam paramam dhyeyam. Knowledge is supreme.
So, looking at this equation 3, there exists an energy if it satisfies this equation. That's all I can say. Okay, so let's look for the trend. What are the trend? Alpha A is very much greater than 1 is the first one. So, which means you all know what is tan hyperbolic in that limit. It can be approximated to 1. Is that right? So, from there you can determine in such a limit that the energy has to be minus mg squared divided by this g. Don't confuse it with this g is the coupling which was in the front of your v of x. Okay. So, this g squared actually tells you that the energy is proportional to g squared. Sometimes you know whether g is positive or negative, the expression is the same. But if you take instead of minus g as plus g in your potential, the concept is gone because the global potential, global minimum potential will be 0. So, you have to have energy positive. So, you cannot have the ground state, bound state. If I take this and flip it, okay, if I make this instead of attractive, I make it repulsive, even though the calculations can go through mechanically, the theorems tells you that these two theorems will prevent you from saying that you cannot have a bound state problem. Okay, bound state has to satisfy this as well as this, and this will not be possible if I put a plus sign here. Okay, so at least for alpha A, alpha times A is the point where you have this delta potential, delta function potential, Dirac delta function. If alpha A is very much larger than 1, you do have an energy solution and you can get that energy value also analytically. But that is only when alpha A is very much larger than 1. What about, so we say that there is a ground state energy for alpha A very much greater than 1 and the ground state energy is minus mg squared by 2h squared. What about alpha A much less than 1? What about that condition? Look at the equation 3 again. So, you can substitute tan hyperbolic alpha A as alpha A and then simplify this above equation and you can show that the energy will be minus twice mg squared. So, in fact, it is doubling. Something wrong? 4 times? Make a mistake? So, this will be alpha A. So, then you will have an alpha A, alpha squared. Anyway, check it. If it is 4, I will check that. Or you want me to do it on the board? Let's try it here. Okay, so I have twice mg h cross squared alpha to be approximately 1 plus alpha A. I have just taken this 1 to the other side. Okay. From here you will get alpha to be twice mg by h cross squared. E will be minus h cross squared alpha squared by 2m, which is minus 2 mg squared by h cross. Have I made a mistake? Someone was saying there is a 4 factor. Okay, so there is a factor of 4 between the alpha A much greater than 1 and alpha A much less than 1. So, we can also do an equivalent solution. As I said, since it is a symmetric potential, instead of even function, we could have also worked with odd functions. So, in the context of odd functions, sine hyperbolic is an odd function and you will also have e to the minus alpha x and minus b e to the power of alpha x for the two regions. So, that this region before A and after A are all odd. Exactly like what we did for the even function. Please redo it again. Wave function continuity, derivative of wave function continuity, and what is expected is that you will get a, instead of that tan function, you would have a cot function. Again, you can do alpha A much less than 1, much greater than 1. In that case, cot hyperbolic is again 1. For large alpha A, there is no distinction. The leading term is e to the alpha A. So, you will have the same as what you got for the even function. So, for very high, if you fix an A and if you want alpha to be very large, that means when minus E, the energy will be very large, magnitude of the energy, then both the even function or odd function don't distinguish. They give the almost the same energy. This is what is the trend we see. For alpha A very much less than 1, take the above equation, the cot hyperbolic function, and find the solution. So, you get alpha to satisfy some condition like this, and I have already said alpha is positive, which means there will be a solution if and only if your A value satisfies this condition. So, for low alphas for a fixed A, if this condition is not satisfied, then you may not get the odd solution, but you will definitely get the even solutions. Even solution energy was minus 2 mg by h cross 2. So, this kind of indicating that at low energies, even solution, the ground state solution will be even and it will be present, and low energies, the odd solution may not be present if A does not satisfy this condition. This is all from math. We tried to put a continuity, we have tried to put a discontinuity in the derivative function. We know what the discontinuity factor is, right? We have substituted and we ended up trying to get an equation which is a cot hyperbolic function, but then we try to find the trend for alpha A to be very much less than 1, and the trend seems to be that if the A value satisfies this criterion, you will find a solution for alpha A less than 1. So, what are the observations? 2 mg by h cross squared, suppose is less than 1 by A. Even solutions will anyway exist, but odd solutions will not be there. So, this should be greater, the second line should be greater than 1 by A, which is this condition. Then both odd and even functions will give bounds. Please correct this, I will also correct it when I put the file. So, this second one should be greater, then both odd and even functions will give bound state. So, this is from algebraic way of doing it and getting the trend, but it will be nicer to actually plot your solutions and see whether you get a non-trivial value for alpha and hence the energy. So, how do we go about it? The graphical analysis. So, it is a similar way in which I am going to do it for this case. So, now I am going to take a define, do not confuse this x with some position or anything, I am calling some variable x as equal to alpha times A, just for convenience. So, the even solution which I have, the solution for the condition satisfied for the energy when you take even wave function solution, that can be rewritten in terms of the x variables. You can also define another variable y as mg A by h cross squared. So, then the above equation will be, this equation can be rewritten by putting an A and an A below. If you do that, then you will have a y, actually it is a 2y I think, the 2 will cancel on both sides. So, it simplifies, this equation can be further simplified, equation 5 can be further simplified, substituting y as y over x proportional to this, and you can write an equation which is e to the minus 2x equal to x over y minus 1. What typically, how do you find a solution to this? I'm incidentally interested in x, and for a specific y, you can take y to be some value because it's dependent on the coupling constant, the position of your Dirac delta function, the mass and h bar squared. It's a constant. Y has nothing to do in the plot. You can fix y to be some value 0.1, 0.2, okay. And you have the right hand side as x by 0.2 minus 1, and left hand side is e to the minus 2x, which is a function of x. Right hand side is also a function of x because y is a constant. So you can plot e to the minus 2x as a function of x. You can plot x by a specific value of y. You can take y to be greater than 1, less than 1, greater than half, less than half, whatever, and you can plot. This is what we do. If both left hand side and right hand side get some intersection point for a specific value of y, that intersection point will give you what is that x, and looking at that x, you know what is alpha, and if you know alpha, you can determine what is the energy. Of course, different A's will give you different alphas, and you can plot graphically and get a solution to the curve. Is that right? So, will you try to plot this yourself when you get back and see what is happening? When does it change? For what values of y? Whether this y plays a role and so on. Okay. It will play a role in the sense that we saw that odd and even function solutions had a requirement that 2mg by h cross squared has to be greater than 1 over a. There is some constraint which will kind of play a role, that there will be a turning point y, below which only even solutions, or above which I don't know, one of them it will not be there. In the other regime, both the solutions will be there. Okay. So please play around with this and get a feel of the solutions. Okay. Similarly, with the cot hyperbolic alpha in the above equation, which is for the odd solution, we got this condition. I am rewriting that condition in terms of the same x and y variable. Okay. Please verify this also. You can see here it is x by y minus 1, this is 1 minus x by y. So the curve itself, as you can see, will have an intercept of minus 1 here, whereas this one will have a slope which is negative. Okay. You can see all these kinds of trend and you can plot them. So what is the ultimate thing I am trying to say? The intersection point of the left hand side curve and the right hand side curve for a specific y will give you the energy for an even solution. Similarly, the intersection point of the right hand side and the left hand side for the odd solution will give you another energy. You can also check whether this energy and this energy are one and the same or different, which one has lower energy, which one has higher energy. All these checks you can do. Okay, so plot three curves for values of y, e minus 2x versus x, x by y minus 1 versus x. Is that the even function? Yes, that's an even function. And 1 minus x by y versus x for the odd function. So you have to check no intersection of odd solution with curve 1 when this y, that condition we already have, if you remember. We had this condition twice mg a by h cross squared is greater than 1 by a. You can take this a this side and then that becomes y greater than half. So solution, odd solution will exist for y greater than half and even solution will exist for y less than or equal to half. Y greater than half, both odd and even will exist, because for any y you will have an even solution. We did not find any condition like this. For the odd solution, if y is greater than half, you will have a solution, but you will not have a solution when y is less than or equal to half also. Is that right? Because alpha has to be positive. So, no intersection of odd solution with curve 1 when y is less than or equal to half. This is what I have tried to show you from the earlier slide. Both odd and even intersect curve 1. This is this curve 1 for y greater than half. Should we plot and check? I have tried to plot it in Mathematica for you. Which curve is what? The blue color line is what? E to the minus 2x. What about this orange color line? Odd solution or even solution? Even solution. It intersects at this point. Is this visible? So, there is a solution, but odd will start is the green line, and the green line does not intersect the e to the minus 2x when y is less than or equal to half. So, this I have tried to plot with some y value as 0.4. 0.4 if I take, then I find this plot. You can try and check. Why are there only 2 solutions? What else can you have? Barrier is infinite, yeah, and it's a delta function. No, but this is also for a specific, it's a Dirac delta function is a spike at x equal to plus a and minus a. So, that kind of triggers a discontinuity, and this is the only possible solutions you get. You can't, when you do a potential well and barriers, you don't get many solutions. No, but you do have for a specific energy of the particle which you send in, you find one solution. For different energies you can, yeah, but depends on the A. It's constrained by the A also. A is given in the problem, so you will have only one specific energy which satisfies that condition. That's what you see. You don't get more than, yeah. See, the thing is, sometimes when you have tan functions, there will be a series of curves. Then there is a possibility of it hits the higher curves. But here it's a exponentially damping curve, and it's impossible for a straight line. I don't see a physical way of arguing that there will be only bound state, but I can think about it. But I know that for other cases, when you have oscillatory solutions in certain regions, which is what happens in the case of your particle in a box and so on, you could have a repeated periodic ones which can kind of give the constraint. So, you can have different energies giving you. But in this case, it's always damping exponential solution in all the 3 regions. So, in such cases, there is no periodicity. So, there is no way in which you can find more than one solution. This is what I see, but I don't, it's not a proof, but this is what I see. Okay. Okay. So, similar thing we can plot for y. So, this is not a very clear plot, but you can still see that the blue curve is the exponential curve, and for y greater than half, the slope of the odd function changes and it hits this curve, right? And similarly, the even function is also hitting this curve. So, what is happening? How do we see which energy is smaller? Here, of course, this energy, when y is less than half, I see the energy to be here, but here the energy is increasing, and this is lower negative. That's true. I agree. Okay. Excellent. So, this is what we see, that the negative energy Brown states is going to be lower for the even wave function than the odd wave function. Okay, it's kind of neat and nice, so I thought I should take this to show it to you on a slide so that it's clearly in your mind and you know when to do a difficult problem, how you should analyze them graphically, and also try to see whether you can analytically go to certain regions like alpha A very much greater than 1, alpha A very much less than 1, and then you get a trend. Once you get the trend, you go back and look at whether the trend is seen for an arbitrary alpha A. So here I have not put in any condition that alpha A has to be less than 1 or alpha A to be greater than 1. Graph gives you what is the alpha or what is the energy, and that I find out by looking at this intersection. And as he was pointing it out, that for bound states generally you will have more than one solution, but if you had in some regions oscillatory solutions, then there could be a periodic kind of curves instead of this exponentially damping blue curve, and then a straight line could cut those periodic curves at many points, and then you can say that you will have bound states when your energy is between the sun, there will be 2 bound states, there will be 3 bound states and so on. But in this case, in the delta function potential, you do see all the 3 regions, you have only the exponentially damping or growing functions. So you will have a single curve, not if you had a tan function, you would have a series of curve between pi by 2 to and a 3 by 2 and so on. So you will start seeing some periodicity, and if you put this other curve of the right hand side, it could intersect those periodic curves at different points. So that's why you may have more than one solution. I think this answers your question. Okay, so I want to give you a couple of other things. How many of you know Fourier transforms? Everybody knows. Okay. And how do you see Fourier transforms in quantum physics? Momentum space. Okay. So let me try and give you a little bit more flavor here, and then we'll stop. So what we have seen is, at least in a particle in a box, we could write psi of x as a linear combination of Cn times psi n of x, where psi n of x are the stationary state solutions to your Schrodinger equation. So this is what we call it as a linear superposition. But we could take wave packet as a superposition of plane waves Plane waves are typically denoted by e to the ikx, free particle. How do I write that? Psi of x, I could write it as, I could take a summation if their k's are distinct, but if the k is continuous going from minus infinity to plus infinity, how do I write this? Integral dk, just like you have a probability amplitude for a state, arbitrary state, to have, you know what is Cn, right? Mod Cn squared is the probability of state to be in psi n of, or have energy. This is what you would say. So similarly, I can put a probability factor times e to the ikx. Of course, there will be some normalization here. Some books follow 2 pi. I'll get back to that. So what have I done? It's exactly similar to a discrete linear superposition. But in the case of a wave packet, you superpose various plane waves of various wave vector or equivalently wavelengths. And if there is a continuous distribution for the wave vector k, unlike here, n is discrete, It goes in discrete steps, that's why we need to put a summation. You could equivalently do a superposition, which is an integration here. So when to put an integration, when to put a summation. So Fourier transform, so this expression is nothing but your familiar Fourier transform you have studied. It's nothing but a solution for a wave packet, which is a superposition of all possible plane waves, with the probability of finding it to have a wave vector k is given by mod of phi k square. Phi k doesn't need to depend on x. Sorry, doesn't need to depend. Why did I put it? Okay, thank you. Yeah, phi k depends on k. To be very precise, it should be depending on k. So formally in all your Fourier transform, you typically would have replaced this by a psi tilde of k. And you will call psi tilde of k as the Fourier transform in the momentum space, and psi of x of psi of x. It's a Fourier transform of psi of x. And there are various other properties of Fourier transforms, you know, right? So I'll give a couple of problems based on this Fourier transform for a free particle, where you can put your k to be h cross squared k squared over 2m to be the energy, and you can rewrite it in terms of that, and you can try and do what is the evolution of psi of xt. But this is the concept, that whenever you have a continuum, you can replace it by a, you can also do an inverse. You can try to find a specific wave number from the superposed wave packet. It's an inverse Fourier transform, and these things are visible when you do quantum physics. Okay. So let me stop here.